You see a white dot racing through the darkness, moving at 209,000 kilometers per hour. Third interstellar visitor ever confirmed. Then NASA looks back through the archive and finds something nobody expected. The satellite already saw it, 2 months before discovery. And when they stack over 9,000 images to check if it was active that far out, they find nothing. No extended coma, no obvious cloud of gas and dust, just a bright point that looks exactly like an asteroid. But here's the thing, the comet was already bright, already active, already dumping material into space at 6.4 astronomical units from the sun. The mystery isn't whether it was awake, the mystery is how it hid what it was doing. Welcome to the story of 3I Atlas and the observations that nobody saw coming. The data from the Transiting Exoplanet Survey satellite, the stacked images that showed a comet pretending to be a rock, and what this tells us about an object that traveled billions of years through the void between stars to reach our neighborhood. If you value documented interstellar astronomy and cometary physics like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. Also, the script is researched and factual. Using sources from the paper titled A Search for Coma in TESS Observations of Interstellar Comet 3. iAtlas published October 2025 in the research notes of the American Astronomical Society by Martinez Palomera and colleagues, and pre-covery observations of 3I Atlas from TESS suggests possible distant activity, published July 29, 2025 on Archive by Feinstein, Noonan, and Seligman, deep archival telescope data that most people never dig into. But these teams went hunting through thousands of frames to reconstruct what the comet was doing months before anyone knew it existed. Now back to the information. July 1, 2025, Rio Hurtado, Chile. The Atlas Survey Telescope picks up an object. Designation A11PL3Z, distance 4.5 astronomical units from the Sun, 670 million kilometers, moving fast, too fast. Astronomers run the orbital solution and the numbers don't close. Hyperbolic trajectory, eccentricity over 6, not bound to the Sun, coming from outside. By July 2nd, the Minor Planet Center confirms it. Third interstellar object, 3I Atlas. After 1I Oumuamua in 2017 and 2I Borisov in 2019. The I stands for interstellar, third visitor in 8 years. But the real story starts 2 months earlier in a dataset nobody was looking at yet. May 7, 2025. The Transiting Exoplanet Survey satellite was watching a patch of sky. TESS hunts planets by measuring brightness dips when they cross in front of stars. It takes images every 2 minutes, thousands of frames. It wasn't looking for comets. But 3. iAtlas drifted through the field and TESS caught it. Nearly continuous observations from May 7 to June 1st, 20 days of data. The comet was already at 6.4 astronomical units, roughly 960 million kilometers from the Sun, out where things shouldn't be active yet. Water ice doesn't sublimate that far out, surface temperature too cold, sunlight too weak. But when researchers went back and pulled those frames, they found the object was already glowing. Magnitude around 19.6, bright enough to detect already awake. Adina Feinstein at Michigan State, Daryl Silliman also at Michigan State, John Noonan at Auburn. They knew TESS had been pointed at that region. They pulled the archive, shift stack method. You move the images to track the object, compensate for its motion across the detector. Then you add them together. Co-adding boosts signal. Thousands of short exposures become one deep image. They stacked over 9,000 frames into 2 separate groups. Early May, late May. The goal was simple. Look for an extended coma. Gas and dust spreading out from the nucleus. The signature that screams comet. They found nothing. No extended coma in either stack. The radial profile was clean, point source, same shape as inactive asteroids in the same field. 4 comparison asteroids with similar motion. All showed the same profile. Narrow, compact, no halo, no fuzz. The team measured brightness versus distance from the center. 3I Atlas matched the asteroids perfectly. No detectable extended structure. At face value, this should mean the object was bare. A nucleus with no activity, a rock tumbling through space, but the brightness said otherwise. Hubble Space Telescope images from July 21 show the object has a coma, a bright, dusty cocoon. Nucleus diameter somewhere between 320 meters and 5.6 kilometers. Can't see the solid core. Too much dust. The coma hides it, so if Hubble sees a coma in July, and the object was already bright in May, then it must have had a coma in May too. The brightness numbers match. Magnitude 19.6 in TESS. Magnitude around 12.5 absolute. consistent with July observations. The comet didn't suddenly turn on between June and July. It was active the whole time. Martinez-Palomera and team published their analysis October 2025. They co-added the TESS images, same shift stack method, over 9,000 exposures, two groups again. They applied radial profile analysis, measured how brightness falls off with distance. Compared to point sources, found no extended coma, but then they cross-checked with Hubble. Hubble detected coma light mixed into the central point spread function, not spread out, concentrated near the nucleus. The conclusion lands hard. If 3I Atlas had sustained activity in May, and the dust stayed near the nucleus instead of spreading out, then the dust ejection velocity must have been extremely low, less than 10 meters per second. Standard comets throw dust at 20 to 100 meters per second. Radiation pressure and gas drag push it away, fast. But if 3I Atlas was ejecting dust at under 10 meters per second, the material would stay close. Tight cloud, no extended tail, no visible halo in the stacks. You'd see brightness, but no structure. What does dust velocity under 10 meters per second mean? Either the gas pressure driving the dust is weak, or the dust grains are heavy, or both. Carbon dioxide sublimates easier than water, lower temperature threshold. At 6.4 astronomical units, carbon dioxide can drive activity. But carbon dioxide gas expands slower than water vapor in terms of drag efficiency. Lower gas production means lower terminal velocity for dust particles. Add large dust particles, tens to hundreds of micrometers, and terminal velocity drops further. Hubble images from July show the coma has large dust grains. Reddish color, several micrometers in radius. Small grains at 1 micrometer radius ejected at 22 meters per second. Large grains at 100 micrometers radius ejected at 2 meters per second. The large grains dominate the scattered light. Slow ejection, tight coma. This is exactly what TESS saw. Brightness without structure, light without extension, a comet hiding as a point source. Now the composition comes in. James Webb, Space Telescope Observe 3 on our Atlas, August 6, 2025. Distance 3.32 astronomical units. NIRSpec instrument, infrared spectroscopy. Results published by Martin Cordner at NASA, Goddard, and team. The coma is dominated by carbon dioxide. CO2 to water ratio 7.6 to 1. Among the highest ever measured in any comet. Most solar system comets run closer to 1 to 10 or 1 to 20. 3I Atlas flips that, 8 times more carbon dioxide than water. Also detected carbon monoxide, carbonyl sulfide. Water ice grains. The carbon dioxide mixing ratio sits 4.5 sigma above the trend for long period comets. Outlier, way off the curve. This explains everything about the early behavior. Carbon dioxide sublimates at temperatures around 60 Kelvin. Water needs closer to 170 Kelvin for significant sublimation rates. At 6.4 astronomical units, equilibrium temperature for a dark comet is around 65 Kelvin, perfect for carbon dioxide, too cold for water. Sphere-X observations in mid-August 2025 captured a massive carbon dioxide coma, extended out to 348,000 kilometers. Symmetric cloud, production rate 9.4 times 10 to the 26th molecules per second, 70 kilograms per second of carbon dioxide. Water production rate upper limit 4.5 kilograms per second. No clear water gas coma detected by Sphere-X. Carbon dioxide dominates by more than 15 to 1 in gas production. Carbon monoxide also suppressed. The carbon dioxide sublimates at lower temperature than water. At 6.4 astronomical units in May, carbon dioxide could drive all the activity. Water stays frozen solid. Carbon dioxide, gas pressure low but steady. Dust grains lifted gently, low velocity, no extended coma. Just a bright compact cloud that TESS saw but couldn't resolve as extended structure. The Swift Observatory caught hydroxyl emission in July and August. Hydroxyl comes from water photolysis. Sunlight breaks water molecules. Hydroxyl glows in ultraviolet. Zexi-Shing at Auburn led the analysis. Water production rate 40 kilograms per second at 2.9 astronomical units. That's far for water activity. Most comets don't show strong water until inside 2 astronomical units. But near-infrared observations by Gemini South and NASA Infrared Telescope Facility on July 5 and July 14 show water ice grains in the coma, large icy chunks, 10 micrometer size. These grains act as extended sources. They absorb sunlight, warm up slowly, sublimate over time, release water vapor even though the nucleus surface stays cold. The icy grains float in the coma and steam, fire hose at full blast, but from debris, not from the surface. This is unusual. Most comets sublimate water directly from the nucleus. 3. I-Atlas sublimates water from ice grains in the Coma. The nucleus releases the grains release the water. Two-step process. Back to TESS. The light curve over 20 days shows no clear rotation period. Most asteroids and comet nuclei rotate, period between hours and days. Brightness varies as different faces reflect sunlight. 3. I-Atlas shows no significant periodic signal. Feinstein and colleagues ran Lomskargel periodogram, checked for peaks, found noise, one possible signal at 28 hours but marginal. Comparison with background pixels shows similar noise. The lack of rotation signal could mean 3 things. 1. The Coma obscures surface features. Dust scatters so much light that rotation changes get washed out. 2. The nucleus is small, and the Coma contributes most of the brightness. Rotation of a sub-kilometer object buried in dust won't show up. 3. The object has low amplitude variation, near spherical shape or uniform surface. Any of these fit? Most likely the Coma hides everything, even in May when activity was just starting. The Coma already contributed more than half the total brightness. By late May, the Coma dominated. 90% of light from dust, 10% from nucleus. You can't detect rotation when dust contributes 90%. The Zwicky Transient Facility caught 3. I-Atlas, starting May 15, 2025. 41 detections through early July. Pre-discovery imaging, distance 6.1 astronomical units on May 15. The brightness stayed flat until early June. Plateau phase. No growth in effective size. Then steady brightening from June onward. Uniform phase. The plateau suggests the nucleus was visible with minimal Coma during the first 2 weeks. Then activity ramped up. Carbon dioxide sublimation increased. Dust production rose. Coma expanded. By July, the Coma diameter reached 13,040 kilometers, according to Vera Rubin Observatory. Observations on June 21, 18,760 kilometers by July 2nd. Growth over 11 days. Expansion rate over 500 kilometers per day. This matches the dust velocity calculations. If dust moves at 10 meters per second, it travels 864,000 meters per day, nearly 900 kilometers per day. Over 11 days, that's 10,000 kilometers of expansion. Close to observed. The numbers work. Hubble constrained nucleus, size July 21. Upper limit, 5.6 kilometers diameter. Lower limit, 320 meters. Can't resolve the nucleus. Too much Coma light. Dust loss rate, 6 kilograms per second of small particles. Consistent with comets first seen at 300 million miles from the Sun, the teardrop shape in Hubble images shows a sunward plume, extended toward the Sun, not away like a tail. This is opposite standard comet behavior. Radiation pressure pushes dust antisolar. Tails point away from the Sun. But 3. I-Atlas shows a bright extension sunward. Factor of 2, longer toward the Sun than perpendicular directions. Eric Keto and Avi Loeb analyzed the geometry. Line of sight to Earth, misaligned with sun direction by only 10 degrees in July. Edge on projection. Geometric correction factor, 5.76. True extension 10 times longer, sunward than wide. This suggests ice fragments sublimating as they drift toward the Sun. Absorb more light on the sunward side. Glow brighter there. Fragments evaporate before radiation pressure sweeps them back. Unusual. Not seen in solar system comets. This could be related to the large ice grains. The 10 micrometer water ice particles detected by Gemini and IRTF. These grains drift slowly. Take time to heat up. Sublimate gradually. Create an extended source of gas around the nucleus. The gas scatters light, appears as a sunward glow. Now the deep question, why no extended Coma in TESS data if the comet was active? The answer sits in dust velocity and angular resolution. An extended Coma needs dust to travel far from the nucleus and sub-10 enough angle to be resolved. If ejection velocity is under 10 meters per second, an observation window is 20 days, dust travels less than 17 million meters maximum, 17,000 kilometers. The Coma diameter in late May was probably around 10,000 kilometers based on interpolation between ZTF plateau and Rubin observations. 10,000 kilometers at 960 million kilometers distance, sub-10's about 2 arcseconds. TESS pixels are 21 arcseconds. The Coma is 10 times smaller than 1 pixel, unresolvable. The light blends into the point spread function, looks like a star. The radial profile shows no extension because the extension is sub-pixel. You need sub-arcsecond resolution to see it. Ground telescopes with adaptive optics or space telescopes with fine guidance sensors. TESS has neither for this scale. This tells us 3. Our I-Atlas runs cold and slow in the outer system. Carbon dioxide drives early activity. Water stays locked. dust grains large and heavy, ejection velocities under 10 meters per second. Coma stays compact, no tail yet. Then as the comet moves inward, water sublimation kicks in at 3 astronomical units. Gas production increases, dust velocity rises, Coma expands, tail forms. By late August, Gemini South images show a clear anti-solar tail, 30 arcseconds long, 56,000 kilometers. Classic cometary tail, dust blown back by radiation pressure. But in May, the comet was cryptic, bright but invisible as a comet in morphology. TESS captured that cryptic phase, the hidden awakening, the beginning that looks like nothing. The composition explains the cold start. Carbon dioxide ice line sits farther out than water ice line. In the protoplanetary disk, where 3 I Atlas formed, it likely condensed beyond the carbon dioxide ice line, region rich in carbon dioxide ice, less water, or the nucleus experienced heavy radiation exposure during its interstellar journey. Cosmic rays and ultraviolet light can alter ice composition, sputter water preferentially, leave carbon dioxide enriched surface. Either way, the 8:1 carbon dioxide to water ratio is extreme. See 2016. R2 is the only other comet close. Most comets sit below 1:5. The extreme ratio suggests formation in a cold region of the parent disk, beyond 5 astronomical units from the parent star, where carbon dioxide ice dominates over water ice. Or it suggests a surface layer depleted in water by radiation processing during billions of years in interstellar space. Both scenarios are possible. Webb observations test this. If the carbon dioxide to water ratio stays constant as the comet approaches the Sun, the bulk composition is carbon dioxide rich. If the ratio decreases, only the surface is carbon dioxide rich and the interior is water rich. December observations will tell. The carbon isotope ratio is Earth-like. Carbon 12 to carbon 13 around 90, similar to solar system values. This means the parent star system had similar carbon chemistry. Formation environment not wildly different from ours in terms of carbon sources. But the carbon dioxide excess suggests either a different location in the disk, farther out, colder, or a different thermal history. One scenario. 3. I Atlas formed near the carbon dioxide ice line where carbon dioxide ice is abundant and water ice less common. Another scenario, heat penetration into the nucleus is inhibited, insulating layer or low thermal conductivity. Carbon dioxide sublimates from the surface. Water stays frozen below. The surface layer controls what we see. Deep interior could be water-rich, but we won't know until the comet breaks apart or until we get much closer observations. Very large. Telescope observations. August 23, 2025 show nickel emission, atomic nickel vapor, no iron detected. Usually, nickel and iron sublimate together from metallic grains. But 3. I Atlas shows nickel without iron. Thomas Puzia at Pontifical Catholic University of Chile led the analysis. The hypothesis: nickel tetracarbonyl, volatile molecule, nickel bonded to 4 carbon monoxide groups, breaks apart easily under ultraviolet light, releases nickel atoms and carbon monoxide. This molecule is rare, not seen in solar system comets. But if present in 3, I Atlas, it explains both the nickel emission and part of the high carbon monoxide abundance. Nickel tetracarbonyl formation requires carbon-rich environment, high carbon monoxide abundance, low temperature. Interstellar space provides all 3. The molecule could form in the dense molecular cloud, where the comet's parent system originated, or during the interstellar crossing. 4 billion years in the cold. Carbon monoxide and nickel atoms meet, bond, freeze into the nucleus. Now sunlight breaks the bonds. Nickel glows in visible wavelengths. Carbon monoxide adds to the gas production. The water ice detection came July 5 into July 14. Gemini South and NASA Infrared Telescope Facility. Binyang led the team. Near-infrared spectroscopy, red slope and optical, 10% per 1,000 angstroms between 500 and 800 nanometers. Typical of D-type asteroids and comets with organic-rich dust. Flattens in near-infrared, 3% per 1,000 angstroms from 900 to 1,500 nanometers. Water ice absorption feature at 2.0 micrometers, broad and shallow. Modeled with 70% Tagish Lake meteorite material and 30% 10 micrometer water ice grains. The Tagish Lake meteorite is carbonaceous, rich in organics and phyllosilicates, low albedo, dark, similar composition to D-type asteroids. The match suggests 3. I Atlas has similar refractory material, carbonaceous organics, silicates, mixed with water ice. The ice grains are large, 10 micrometers. Spectral signature matches laboratory measurements of 10 micrometer ice particles. These grains form in the Coma. Nucleus releases them as frozen chunks. They drift outward, sublimate slowly, extend water vapor production beyond the nucleus surface. The 1.5 micrometer water ice band is not detected. Signal to noise too low, or dilution by refractory material. But the 2 micrometer band is clear. Water ice confirmed. First time water ice spectroscopically confirmed in an interstellar object's coma. Borisov showed hints, but not definitive. 3. I-Atlas shows definitive water ice absorption. The orbital mechanics point to ancient origin. Hyperbolic excess velocity 58 kilometers per second. Unbound to the sun, came from interstellar space at high speed. Eccentricity 6.2, extremely hyperbolic. When traced backward, the orbit doesn't converge on a single star. The comet has been in the galaxy for billions of years. Gravitational kicks from passing stars add velocity. Drift through the Milky Way, velocity built up over time. Trajectory analysis suggests origin in the galactic bulge region. Stars formed around 7 billion years ago. 2.5 billion years before our sun. That makes 3 I-Atlas potentially 7 billion years old. Oldest comet ever observed, formed around a star that ignited when the Milky Way was younger and less enriched in heavy elements, then ejected from that system. Wandered through the galaxy, crossed the space between suns, thousands of light years, millions of years, finally intercepted by our sun's gravity. Well, pure chance, random encounter. The speed is the giveaway. 209,000 kilometers per hour relative to the sun. Fastest solar system visitor on record. Every gravitational encounter adds velocity. Pass near a star, gain speed through slingshot effect. Pass through a stellar cluster, multiple small kicks. Drift through spiral arm, gravitational tide from dense star field. All of it adds up. The longer the journey, the higher the speed. 3. I-Atlas has been traveling so long its velocity dwarfs anything native to the solar system. Long-period comets from the Oort cloud enter at tens of kilometers per second. Typical value, 20 to 30 kilometers per second. 3. I-Atlas enters at 61 kilometers per second, double or triple the speed. This is the signature of deep time, billions of years accumulating velocity, billions of years crossing the galaxy. Now back to TESS and the non-detection. The October 2025 paper by Martinez Palomera and colleagues makes it explicit. No extended coma detected in TESS data, despite co-adding over 9,000 images. Radial profiles comparable to inactive objects. But brightness consistent with coma light concentrated in the central point spread function. If activity was sustained for any significant time during the observations, dust ejection velocity must be under 10 meters per second. This is the key finding. 3. I-Atlas was active at 6.4 astronomical units, but the activity was subtle. Low velocity dust, compact coma, invisible to TESS as extended structure, but visible as brightness. The comet hid in plain sight, looked like an asteroid in morphology, glowed like a comet in photometry. This dichotomy reveals the physics: low gas production, large dust grains, slow terminal velocities, tight coma, subpixel extension. Why does this matter? Because it changes how we search for interstellar objects. TESS and other surveys detect brightness. They flag objects that move, but morphology analysis, looking for extended coma, requires deeper stacks and higher resolution. An object can be bright and active, but show no extended coma if dust velocities are low. This means surveys could miss active interstellar comets in the outer system if they rely on coma morphology alone. Brightness? Photometry alone isn't enough to confirm cometary activity. Morphology alone isn't sensitive to low velocity dust. You need both. You need spectroscopy. Carbon dioxide emission lines, water ice absorption bands, cometary volatiles, the diagnostic signature. Without spectroscopy, an object like 3 I-Atlas in May looks like an asteroid, bright point source, no structure, moving, could be main belt asteroid, could be Trojan, could be Centaur, could be interstellar comet. Only spectroscopy and velocity measurement separate them. The TESS observations also constrain the onset of activity. The object was bright in early May, magnitude 20.83 in the first stack covering May 7 to May 20. Magnitude 19.28 in the second stack covering May 20 to June 1st, brightening by a factor of 5 over 3 weeks. Factor of 5 is 2 magnitudes. Large change. This suggests activity increased significantly during the TESS observation window. Not a sudden outburst, gradual ramp up. Carbon dioxide sublimation starting slowly, dust production increasing steadily, coma forming and growing, but still confined to small radius. No extended structure yet. By late May, the brightness peaked relative to expected nucleus contribution, then held steady through early June according to ZTF data, plateau phase, production rate matched escape rate, equilibrium, then resume brightening in late June and early July. This two-phase behavior, ramp up, then plateau, then ramp up again, suggests thermal inertia effects. The nucleus takes time to heat up. Carbon dioxide sublimation starts when surface temperature reaches 60 Kelvin, but the interior lags. Heat penetrates slowly. Sublimation rate limited by heat flow. Takes weeks for thermal wave to propagate inward. Once equilibrium is reached, sublimation rate stabilizes. Then, as heliocentric distance decreases further, temperature rises again. Sublimation rate increases again, second ramp-up phase. If you value deep space research and evidence-based astronomy like this, make sure you're subscribed. Every subscription supports the work we do. Drop a comment with your location so we can see where this story reaches. Now let's continue. The brightening curve also rules out certain scenarios. If the object were an inactive asteroid that just happened to be bright, brightness would stay constant or decrease slightly with phase angle changes. Instead, brightness increased by factor 5. Clear signature of activity. If the object had a sudden outburst, impact, or internal pressure release, brightness would spike, then decay. Instead, brightness ramped up gradually. Clear signature of sublimation onset. If the object were fragmenting, brightness would increase, then show multiple components in high-resolution images. Hubble shows single component, no fragmentation. The brightening is sublimation-driven activity increasing with temperature as heliocentric distance decreases, standard cometary behavior, but starting unusually far from the Sun due to carbon dioxide dominance. The absence of a clear rotation period in TESS data also constrains the nucleus properties. If the nucleus were bare and irregular, rotation would cause brightness variations. Amplitude depends on axis ratio and albedo variation. Typical amplitude 10 to 50% for elongated objects. Period hours to days, none detected. Either the nucleus is nearly spherical, or the surface has uniform albedo, or the coma dominates brightness. Third option most likely. Even in early May, the coma contributed significant light. By late May, the coma dominated, 90% coma light. 10% nucleus light. Rotation modulation of 10% signal is smaller than photometric noise. TESS, photometric precision for magnitude. 20 objects is around 5% per 2-minute exposure. Stacking improves precision, but not enough to detect 10% modulation on top of 90% constant coma background. The rotation is there, hidden, buried in coma light, undetectable. Compared to 2I Borisov, discovered August 2019 at 3 astronomical units, already active with visible coma, water-driven activity, nucleus diameter around 500 meters, production rate modest, comparable to Jupiter family comets, no clear rotation period detected, coma dominated. 3I Atlas is similar but more extreme, larger coma in absolute size. Carbon dioxide-driven activity instead of water. Higher gas production rates for carbon dioxide, lower for water. Composition inverted compared to Borisov. Borisov was a water comet with some carbon dioxide. 3I Atlas is a carbon dioxide comet with some water. The formation environments must differ. Different regions of different disks around different stars, different chemistry. Borisov likely formed inside the water ice line where water dominates. 3. I Atlas likely formed outside the carbon dioxide ice line where carbon dioxide dominates. Or Borisov formed in a water-rich disk, and 3I Atlas in a carbon dioxide-rich disk. Disk composition varies between stellar systems. Metallicity, carbon to oxygen ratio, location and galaxy, all affect disk chemistry and planet formation outcomes. The nickel tetracarbonyl hypothesis adds another layer. If confirmed, this would be the first detection of an organometallic molecule in a comet, complex molecule. 4 carbon monoxide groups bonded to 1 nickel atom, forms in industrial processes on Earth, used in nickel refining. Purification. But in space, the formation mechanism is different, requires carbon monoxide gas and nickel atoms at very low temperature. Below 100 Kelvin, interstellar clouds provide perfect conditions. Carbon monoxide is the second most abundant molecule after molecular hydrogen. Nickel atoms come from dust grain sputtering. Cosmic rays hit silicate or metal grains, knock off atoms. Atoms drift in gas phase, collide with carbon monoxide molecules, stick, form nickel carbonyl, freeze onto grain surfaces. The comet's parent protoplanetary disk could have inherited interstellar material rich in nickel tetracarbonyl, or the comet itself formed the molecule during its interstellar journey. 4 billion years is more than enough time for surface chemistry, radiation processing. Atom by atom construction, molecule by molecule accumulation, Mars. Reconnaissance, orbiter will image. 3I Atlas on October 3, 2025. High-rise camera, half-meter aperture. Distance 29 million kilometers from comet. Pixel resolution 30 kilometers. The Coma is 300,000 kilometers across by then, 10,000 pixels wide. Easily resolved. The nucleus, even if 5 kilometers, fits in 1 pixel. But the Coma is optically thin, transparent. Optical depth much less than 1. Light from the nucleus passes through with minimal absorption, hits the detector. The central pixel brightness equals nucleus brightness plus line of sight integrated Coma brightness. If we model the Coma, assume symmetric power law density profile falling as radius to the -2, we calculate expected Coma contribution to central pixel. Subtract it. Residual is nucleus brightness. Convert brightness to cross-section. Divide by assumed albedo, get nucleus radius. If the nucleus is 1 kilometer and albedo 5% tar, it contributes certain brightness. If 5 kilometers and albedo 5% tar, different brightness. The measurement will constrain nucleus size to factor of 2 instead of current factor of 17. Major improvement. Ends the ambiguity about whether 3I Atlas is small like Borisov or large like early estimates suggested. The James Webb Space Telescope will observe again in December 2025 after perihelion. Post-perihelion observations at around 1.7 astronomical units outbound. Chemistry will have changed. Water production will have peaked during perihelion passage. Carbon dioxide production may drop if surface layers depleted. Dust production increases, then decreases. The Coma composition shifts. More water-rich post-perihelion. Webb will measure the new composition. Compare to August observations pre-perihelion. Track the evolution. See how the carbon dioxide to water ratio changes with heliocentric distance and thermal history. This tests formation models directly. If the ratio stays high around 8:1, the bulk nucleus composition is intrinsically carbon dioxide rich throughout. If the ratio drops to 3:1 or lower, only the outer layers are carbon dioxide rich and the interior is water rich. Surface mantling, differentiation, layered structure. The data will decide between these scenarios: bulk composition versus layered composition, ancient formation signature versus processing signature. Hubble will run ultraviolet spectroscopy in November 2025. Measure sulfur to oxygen ratio in the Coma. Detect sulfur-bearing molecules with high precision. Carbonyl sulfide already confirmed by Webb. Hydrogen sulfide might be present but not yet detected. Sulfur dioxide, possible. Sulfur chemistry in comets traces formation, temperature, and oxidation state. High sulfur relative to oxygen means cold, reducing formation. Environment. Low sulfur means warm oxidizing environment. 3. I-Atlas shows carbonyl sulfide at detectable levels. Sulfur confirmed. The sulfur to oxygen ratio will constrain the temperature and redox conditions of the parent disk region where the comet formed. Cold outer disk, beyond 10 astronomical units, or warmer mid-disk, around 5 astronomical units. The ratio varies by factor of 10 between these regions. Measurement precision will reach 10%, enough to distinguish formation regions. Combined with carbon dioxide to water ratio and carbon isotopes, the full formation picture emerges. Temperature, pressure, redox state, radial distance from parent star, all encoded in chemistry. Now, the final piece. What does this mean for interstellar object population statistics? 3. I-Atlas is the third confirmed. Oumuamua in October 2017. Borisov in August 2019. 3. I-Atlas in July 2025. 3 detections in 8 years. Spacing is irregular. 2 years between first and second, 6 years between second and third, but detection capability has improved. Pan-stars found Oumuamua. Gennady Borisov with a 65 centimeter telescope found Borisov. Atlas with a 50 centimeter telescope found 3I. Atlas. Smaller telescopes finding objects means they're getting brighter on discovery or we're getting better at detecting them. 3. I-Atlas was magnitude 19 on discovery. Borisov was magnitude 17, brighter. Oumuamua was magnitude 19.5, similar to 3 older I-Atlas. Discovery magnitude depends on many factors: heliocentric distance at discovery, phase angle, Coma brightness, size, albedo, all variable. But the trend suggests detection improving. The Vera Rubin Observatory comes online late 2025. 8.4 meter primary mirror. 3.5 gigapixel camera, deep survey, LSST, legacy survey of space and time. Rubin will detect interstellar objects at much greater distances and fainter magnitudes than current surveys. limiting magnitude around 24.5 in stacked images. Compared to ATLAS, limiting magnitude around 19.5, 5 magnitudes deeper. That's factor of 100 in brightness, factor of 10 in distance. Rubin will detect interstellar objects at 10 astronomical units instead of 4. Earlier in approach, more time for follow-up. Better orbits, more observations. Predictions suggest Rubin will find 1 to 10 interstellar objects per year once fully operational. Maybe more. The population is there. We just haven't been looking deep enough or wide enough. Rubin looks deep and wide. 7 square degrees per pointing. Image the entire visible sky every few nights. Cadence optimized for moving objects. Interstellar visitors will light up the Discovery pipeline. Not dozens per year, but several. Enough to characterize the population, enough to measure size distribution, composition distribution, velocity distribution, orbital element distribution, all the statistics needed to connect interstellar object population to galactic structure and planet formation processes across the galaxy. TESS data tells us some of these objects will be cryptic. Bright, but no extended coma, visible in moderate resolution data. Active, but morphologically invisible at coarse pixel scales. Traditional surveys flag them as asteroids or unknown transients. Follow-up spectroscopy reveals the truth. Carbon dioxide emission, water ice features. Hydroxyl bands, interstellar velocity, hyperbolic orbit. The more we look, the more we find, and the more we find, the more we learn. Each interstellar visitor is a sample from another planetary system, a piece of another star's formation, history, delivered to our doorstep by chance. Random cosmic billiards across billions of years. We catch them briefly, months, then they're gone. But the data stays, the spectra, the images, the light curves, the measurements, forever archived, forever available for reanalysis, future techniques, better calibrations, new models. The data ages like wine, gets better with time. 3. iAtlas carries a message written in molecules, carbon dioxide, ice, water ice grains, nickel, tetracarbonyl, organic tholins. The message says planetary systems form around stars throughout the galaxy. They make small bodies. Icy planetesimals, comets, then eject them. Gravitational scattering, close encounters with giant planets. The small bodies escape, wander interstellar space, accumulate cosmic ray damage, alter their surfaces, preserve their interiors. Billions of years later, a tiny fraction passes through another system, our system, glows in sunlight, sublimates, releases molecules frozen since formation. We measure those molecules, read the formation conditions, temperature, pressure, chemistry, location in parent disk, type of parent star, age, all encoded, all readable if we have the instruments and the time. The TESS observations capture the beginning. The moment 3, iAtlas woke up. May 7, 2025, 6.4 astronomical units, surface temperature reaching 60 Kelvin, carbon dioxide sublimation threshold, gas escapes, lifts dust, coma forms, compact, tight. Dust velocity under 10 meters per second. No extended structure visible, just brightness, magnitude 20, declining to 19.3 over 3 weeks, factor of 5, increase. Activity ramping up, temperature rising, sublimation accelerating, but still cryptic, still hidden as a point source. TESS, pixels too coarse, coma too small. Angular size 2 arc seconds, pixel size 21 arc seconds, subpixel structure unresolvable. The light is there. The coma is there. The activity is there, just invisible as extension. And when researchers stacked 9,000 images and measured radial profiles and compared to asteroids and found no difference, they didn't stop. They kept pushing, cross-checked with Hubble, realized coma light was in the point spread function, calculated dust velocities needed to keep coma compact, under 10 meters per second, compared to observed large dust grains in later Hubble images, 2 meters per second for 100 micrometer grains, 22 meters per second for 1 micrometer grains. The numbers matched. The physics worked. Low velocity dust from low gas production and large grains. Carbon dioxide at 6 astronomical units produces modest gas flux, tens of kilograms per second, not hundreds. Modest flux means modest drag. Large grains means high mass. High mass divided by modest drag equals low terminal velocity. Under 10 meters per second, the dust lifts off, escapes nucleus gravity, but doesn't fly far. Stays within 10,000 kilometers, forms compact coma. Invisible as extended structure. Visible as brightness. Perfect camouflage. The October 2025 paper is 12 pages, 3 figures, 1 table, Lead author Juan Martinez Palomera at University of Barcelona. Co-authors Christina Hedges at NASA Ames and Avi Loeb at Harvard. Published in Research Notes of the American Astronomical Society. The analysis is methodical. Stack images in 2 temporal groups, extract photometry, measure radial profiles, compare to known asteroids, conclude no extended coma detected, cross-reference with Hubble observations. Note brightness consistent with Coma in central PSF. Calculate dust velocity upper limit, 10 meters per second, discuss implications, active comet with compact coma due to low ejection velocities. Simple, clean, definitive. The paper doesn't speculate wildly, doesn't claim alien origin, doesn't sensationalize, just presents data, presents analysis, presents conclusion, science as it should be done. The July 2025 paper by Feinstein, Noonan, and Seligman goes deeper into the light curve, 20-day baseline. Magnitude measurements every 2 minutes stacked into nightly averages. Brightness evolution tracked. Early magnitude 20.83, late magnitude 19.28, factor 5, brightening, periodogram analysis for rotation, no significant peaks. Upper limits on rotation amplitude, discussion of coma dominance, connection to later observations, absolute magnitude calculation, 12.5, consistent with July ground-based observations. Conclusion that 3, I-Atlas, was active out at 6.4 astronomical units. Possibly the most distant activity onset for any comet ever observed in real time. Carbon dioxide driven, water frozen. The paper is longer, 20 pages, 6 figures, 2 tables, more detailed, more comprehensive, submitted to astrophysical journal letters, peer review in progress. Will be published early 2026. The data is gold, earliest precovery photometry of an interstellar object, earlier than ZTF, earlier than any ground telescope. TESS caught it first. Nobody knew for 2 months. Now layer in the context of other comets. Solar system comets typically activate inside 3 astronomical units for water-driven activity. Jupiter family comets activate around 2.5 astronomical units. Long-period comets from Oort, Cloud, activate around 3 astronomical units. Some show faint activity at 4 astronomical units, but rare. Carbon dioxide-driven activity can start farther. Some comets show carbon dioxide activity at 5 or 6 astronomical units. But these are unusual. Most comets are water-dominated. 3 in I-Atlas is carbon dioxide-dominated. Extreme case. The farthest robust activity detection at 6.4 astronomical units. Temperature 65. Kelvin, below water sublimation. Right at carbon dioxide sublimation. The comet is tuned to carbon dioxide. Bulk composition, surface composition, thermal properties. Everything optimized for carbon dioxide sublimation at large heliocentric distance. This tells us about formation location. Cold disk, far from star. Carbon dioxide, ice abundant. Water ice, less so. The parent star system had different chemistry, or the comet formed farther out than typical solar system comets. The dynamics are also revealing. 3 I-Atlas entered the solar system from the direction of Taurus constellation. Trajectory traced backward goes up out of the ecliptic plane at steep angle. Inclination around 160 degrees. Retrograde orbit, going opposite direction compared to planets. This is typical for interstellar objects. They come from random directions, not aligned with ecliptic. Not in prograde orbits, random orientations. 3. I-Atlas happened to pass near the ecliptic plane for a few months. June through November 2025. Lucky geometry. If it had passed above or below the ecliptic plane, it would have been farther from Earth and fainter. Harder to detect. We got lucky. The trajectory brought it within 1.8 astronomical units of Earth. Closest approach, September 20th. Distance 270 million kilometers. That's close for an interstellar object. Oumuamua passed within 0.2 astronomical units of Earth. Closer, Borisov passed within 2.0 astronomical units, similar to 3 I-Atlas. Close passes are rare but not impossible. The solar system is small. Interstellar objects zoom through in months. Most pass far from Earth, undetectable. We see the bright ones, the close ones, the lucky geometry cases. For every detected interstellar object, hundreds or thousands pass through undetected. Too faint, too far, wrong timing. Statistical models estimate one interstellar object larger than 100 meters passes inside Neptune's orbit per year. Most go undetected, too faint. Discovery rate is maybe 1 per 3 years currently. Will increase to several per year with Rubin. The population is vast. Trillions of interstellar objects in the galaxy. Most never enter another planetary system. drift forever in interstellar space. Dark, cold, invisible. A tiny fraction enters a system like ours, lights up briefly, observed if we're lucky, then gone. The galaxy is full of ancient, frozen planetesimals wandering the dark. 3. I Atlas is 1, 7 billion years old. Formed when the Milky Way was younger, ejected, wandered, entered our system, glowed, measured, departed, back to the dark. Next encounter, maybe another 10 million years. Maybe never. The odds are long. The galaxy is big. But for a few months we had it. We pointed everything at it. Ground telescopes, space telescopes, optical, infrared, ultraviolet, radio, every wavelength, every technique, photometry, spectroscopy, polarimetry, imaging, time series. We measured its position, its velocity, its brightness, its spectrum, its color, its coma size, its tail length, its nucleus size range, its composition, its production rates, its dust properties, its gas properties, its rotation or lack thereof, its thermal properties, its age estimate, its origin estimate. Everything we could measure, we measured. The data set is immense. Dozens of telescopes, hundreds of observations, thousands of spectra, millions of photons captured and analyzed, all for one object, one comet, one visitor from beyond. And TESS gave us the foundation, the earliest data. The precovery observations that show activity started at 6.4 astronomical units with compact coma and low dust velocities, and no extended structure visible, but brightness increasing by factor 5 over 3 weeks, and no rotation period detected because coma dominated and everything hidden in the point spread function until researchers went back months later and extracted the signal and realized the comet was there all along. Active, glowing. Invisible as a comet, but visible as a bright, moving object. The perfect ambiguity. The hidden awakening. The beginning that looks like nothing but means everything. This is the story. 3. I Atlas woke up in early May. TESS watched but didn't know. The comet moved inward, brightened, grew a visible coma by July. Atlas survey spotted it, confirmed interstellar origin. The world noticed, follow-up observations flooded in, composition measured, size constrained, activity characterized. Then someone remembered TESS had been watching that region. Archive search, data retrieved, images stacked, object found, brightness measured, structure analyzed, nothing extended detected, but brightness present. Conclusion, compact coma, low velocity dust. Carbon dioxide driven activity. The story complete, beginning to end, May to October, discovery to perihelion, data from first awakening to peak activity, all recorded, all analyzed, all understood. The implications extend beyond one comet. The TESS observations prove that active comets can hide as point sources in moderate resolution surveys, that compact comas exist, that low velocity dust is real, that carbon dioxide driven activity at 6 astronomical units produces different signatures than water driven activity at 3 astronomical units, that interstellar objects can be chemically extreme, that formation environments vary between stellar systems, that billions of years in interstellar space alter surfaces but preserves interiors, that cosmic rays create complex molecules like nickel tetracarbonyl, that water ice grains can sublimate in comas creating extended sources, that rotation periods can be hidden by coma light, that recovery observations extend baselines and improve constraints, that archive searches matter, that every telescope matters, that every observation matters, that interstellar visitors teach us about planet formation across the galaxy, that we live in a galaxy full of ancient wanderers, that some pass through our system, that we can measure them if we're ready, that we are ready, that we're getting better, that Rubin will find more, that the future is bright for interstellar object science. 3. I Atlas is a data point, one measurement, one sample, but a crucial one. The first carbon dioxide dominated interstellar comet, the first with confirmed water ice grains in the coma, the first with nickel emission suggesting nickel tetracarbonyl, the first observed by TESS before discovery, the first with compact coma and low dust velocity documented, the first with activity onset at 6.4 astronomical units measured in real time, the first with 8:1 carbon dioxide to water ratio, the first that hid in TESS data as a point source despite being active, the first that required archive search and careful analysis to reveal its early behavior, the first with all these firsts, not the last, more will come. Rubin will find them, we'll measure them, we'll learn from them. Each one teaches, each one adds to the picture. Each one constrains models, each one reveals the galaxy's diversity, and in the end, When 3 I-Atlas disappears beyond Jupiter's orbit in late 2026, when it fades below detection limits, when it returns to the darkness between stars, the data will remain. The TESS light curve from May, the ZTF detections from May through July, the Rubin prediscovery images from June, the Atlas discovery images from July, the Hubble high-resolution images from July and August, the Webb spectra from August and December, the Sphere-X composition maps from August, the Swift hydroxyl detections from July and August, the Gemini and IRTF water ice spectra from July, the VLT nickel emission spectra from August, the high-rise nucleus constraint from October, the ground-based photometry from hundreds of observers, the professional spectra from dozens of telescopes, all of it archived, all of it public, all of it available for future analysis. Future students will write theses on this data. Future researchers will find things we missed. Future models will explain things we don't yet understand. The data is immortal. The comet is temporary. The data outlives the visit. That's the power of astronomy. That's the power of archives. That's the power of careful observation and rigorous analysis. That's the power of going back through old data and finding hidden treasures. That's the power of TESS, watching a patch of sky for planets and accidentally capturing a comet from another star. That's the power of researchers who don't give up when they don't see extended Coma, but push forward and realize the Coma is there, just compact, just hidden, just waiting to be understood. That's the power of cross-checking. That's the power of collaboration. That's the power of science. The TESS observations of 3 I-Atlas are now textbook material. Example of compact Coma, example of low-velocity dust, example of carbon dioxide-driven activity, example of archive science, example of precovery observations, example of careful analysis, example of how to extract weak signals from noisy data, example of how to interpret null results as meaningful constraints rather than failures, example of how to combine data sets from multiple telescopes, example of how to connect early behavior to later observations, example of how to build complete picture from fragmentary data, example of how science works when done right: observe, archive, retrieve, analyze, interpret, publish, repeat, simple, effective, powerful. And the final answer to the question nobody asked but everyone wondered: how does a comet hide? It moves dust slowly, under 10 meters per second, stays compact, under 10,000 kilometers radius, sub-10 small angle, under 2 arc seconds, falls below resolution, below pixel scale, blends into point spread function, looks like star, looks like asteroid, but glows brighter than expected, brightens over time, increases by factor 5 in 3 weeks. That's the tell, that's the signature, not morphology. Brightness evolution, not structure, photometry. The comet was never truly hidden. It was always visible, just not as a comet, as a bright point, as an anomaly, as something worth checking. Someone checked, stacked 9,000 images, found it, measured it, understood it, published it. Now we know. Active comets at 6 astronomical units with carbon dioxide dominance and large dust grains look like asteroids in test data, but glow like comets and brighten over time, and that's how you find them. And that's how you know, and that's what 3 I-Atlas taught us before anyone even knew its name.